Hello, and welcome to this section of HUP 112, Logic and Philosophy. My name is Dr. Richard Brown, and this week we are continuing our discussion of natural deduction, and we're going to learn the 5 remaining rules of replacement. So remember what we've been doing so far. We've been learning the rules for constructing proofs for different arguments. We have 2 kinds of rules so far. We have rules of implication, and these allow us to derive one conclusion from a set of 2 premises. And then we have our rules of replacement, or axioms of replacement. And these tells us basically which strings of symbols are equivalent to which other strings of symbols. So you may recall from last time that we have our modus ponens, we have our modus tollens, we have our disjunctive syllogism, and our hypothetical syllogism. In addition to that, we have our other rules of implication, which are constructive dilemma, simplification, conjunction, addition. So these are our rules of implication here. And then we have our rules of replacement. Last week what we talked about was De Morgan's rule, commutativity, associativity, and double negation. So today what we're going to be doing is, in addition to having these at our disposal, we will also add 5 other rules of replacement. And those 5 other rules of replacement that we're going to be adding, transposition, and that says that if you have P horseshoe Q, that's logically equivalent to not Q horseshoe not P. You flip the P's and the Q and you add a negation sign. And again, you can verify these with the truth tables. And so let's quickly do that just to make sure that this is correct. And so we'll just do the quick version of the truth table here. We do true, true, false, 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 true, false, true, false. We add, wherever we see the 1, we copy it down. So here's Q, true, false, true, false. Here's P, true, true, false, false. So now we've written down those, we've copied them over. Now we've used the tilde here to reverse them. So this is going to be false, and that's going to be false, and that's going to be true, and that's going to be true. These get reversed. That's false, that's true, that's false, that's true. Now we compute the value for the horseshoe operator using our 2 negated here. So false, false, that's true, true, false, that's false, false, true, that's true, true, true with the horseshoe, that's true. So we get our true, false, true, true is the truth value for this statement, or possible truth values for this statement. And of course over here we simply compute by the horseshoe rule, and we know what that is. It's true, false, true, true, and there we have it. And you can see that every line of the truth table here is indeed exactly the same. And by the definition of logically equivalent statements, such that they are equivalent when they have every line of their truth tables identical, their main values that is, these obviously will be different, but the main value computed overall will be the same. And so these 2 statements mean the same thing truth functionally. They have exactly the same truth value, and therefore wherever we see one, we can write the other, and vice versa. Remember, these rules, unlike the other rules, go both ways. Now what's interesting about this rule is that we can see something which might be kind of shocking and surprising at first, but which is the case. So take our rule modus ponens. We have P horseshoe Q, and if you have P, then you can infer from that Q. And take our rule modus tones. It says if you have P horseshoe Q, and if you have not Q, then you can derive not P. So these two argument forms look different, and in fact we have two separate rules corresponding to these two argument forms. But what's interesting is, given what we just proved, that this statement is logically equivalent to that statement, well, we can show that these really are versions of the same argument. So if we have P horseshoe Q, we know that's equivalent to tilde Q horseshoe tilde P. So we could replace that with that and have an argument with the same properties. So if we write tilde Q horseshoe tilde P, replacing our first premise here, keep our second premise the same and our conclusion the same, well, it looks like what we have here is a version of modus tollens. Because remember, P is logically equivalent via double negation to tilde tilde P. And Q is logically equivalent via double negation to tilde tilde Q. So what we have here is P horseshoe Q tilde P, therefore tilde Q. So we took what was a modus ponens and we turned it into a version of modus tollens using transportation. And of course you should be able to see that exactly the same procedure could turn any version of modus tollens into a version of modus ponens. Because here, again, P horseshoe Q can be replaced by tilde Q horseshoe tilde P, our second premise, tilde Q, our conclusion, tilde P. And again, what we have here is a P horseshoe Q situation. And this asserts P, those are the same. And this asserts Q. And so what we have taken a modus tollens argument and turned it into a modus ponens argument. And that may be a bit surprising. But one of the things that we should remember is that any valid argument can be summarized in a form that makes it a tautology by conjoining the premises into a conjunction and horseshoeing it to the conclusion. So that this can be represented as a conditional as P horseshoe Q dot P horseshoe Q. So if you do the truth table for this statement here, you will find out that it is a tautology. There is no way of making this false. And one of the interesting things that we have so far discovered is that a statement is logically equivalent to another statement when they have the same value under every possible interpretation. So this statement has the same truth value as any logically equivalent statement, and any logically equivalent statement is simply going to be any tautology. Given that modus tollens is a valid argument, we could also write P horseshoe Q dot tilde Q and horseshoe that to a tilde P, and that's also going to be a tautology. So these two statements should, in some sense, since they're both tautologies, in some sense they should be logically equivalent to each other. And what we've just been able to prove is that, in a sense, they are logically equivalent to each other, because you can always turn one into the other using the rules of transposition. Now that's a bit of an interesting fact, but we'll table that for now and simply point out that we need this rule and we will use it a lot. So in addition to transposition, we will also be using a rule called implication. Implication. And implication is also a rule for dealing with the horseshoe. And what it tells us is that not only can you flip it around like transposition says, but you can turn it into a disjunction. And so that P horseshoe Q is logically equivalent to not P or Q. Tilde P wedge Q. And again, we can do our truth tables. We know what this is going to be. It's going to be true, false, true, true. That's just simply by the definition of the horseshoe operator. And remember, this is, I'm just keeping it in my head. It's easier. It's true, true, false, false, true, false, true, false. So these get reversed. That's false, false, true, true. These get reversed. False, true, false. Excuse me, these don't get reversed. These get reversed because of the tilde, and the Q terms over here stay the same because we're not having a tilde, so we prove true, false, true, false. We compute the value for the wedge operator here, And as long as one or the other of them is true, the whole statement is true. If they're both false, the whole statement is false. So here we have false, true. One of them is true, makes it true. False, false, that makes it false. True, true, that's true. True, true, that's true. And again, you can see they have exactly the same truth values. So these statements are logically equivalent to each other. And what that shows, of course, is that we can turn disjunctive syllogism. Into a version of modus ponens modus tollens or modus ponens if we wanted to. So suppose that we had the argument tilde p wedge q, and then we had tilde p, and so we conclude from that q. And basically what we've done there is a version of disjunctive syllogism. This says a wedge b, tilde, that denies that, so you infer the other one. But now, of course, we've just realized that, or proved, that this is equivalent to that, so we can rewrite that premise as p horseshoe q. Here we have tilde p and conclusion q, but by double negation, we know that tilde p is logically equivalent to simply p, and so we have turned what was a version of disjunctive syllogism into modus ponens. And so once again, this is a tautology, this is a tautology, these two things are logically equivalent. And so really what we're sort of showing here is that if we wanted to, we could reduce this number of things over here. And modus ponens or modus tollens, whichever one you liked, could serve as the sole rule, but it just makes it easier, more intuitive, more human-like to have these logically equivalent ways of doing things. It really is simply a convenience for us to do that. Okay, so now we need a couple more rules here dealing with the horseshoe, and the next one is equivalence, and this deals with the triple bar, which we haven't talked about. That's supposed to be an I right there. We haven't talked about a lot, but you do see triple bars, P if and only if Q, and that's going to be logically equivalent to the conjunction of the two conditionals, P horseshoe Q dot Q horseshoe P. So that just tells you that it's the horseshoe this way, P horseshoe Q, and also that Q horseshoes P. But of course, we now know that we can do it this way as well, and so we can represent it as a disjunction if we wanted to. And so we can also say that P triple bar Q is logically equivalent to not only the two horseshoeing ways, but also to this P dot Q wedge tilde P dot tilde Q. And you might think that's a weird way to put it, but really that just captures the truth table for this operator. So you may recall that the triple bar is true. Well, let me just write out the truth table really fast. True, false, true, false. So the triple bar tells us that the whole statement is true when either it is the case that the two things are true or the two things are false. So it's true when both of them are true, it's true when both of them are false, and it's false if one or the other of these is the case. And that's because that's going to make this one of these conditionals false, and that's okay. So what this is basically telling us here is that one or the other two cases happens. Either you get them both true, which is this case right here, or you get them both false, which is that case right there. So this kind of just captures the actual truth table for the triple bar operator, whereas this captures the kind of more intuitive meaning that if and only if means if and only if. Okay, so, and you will need to use both of those. There are occasions, I'm sorry, why did I erase that? There are occasions where you will need to use both of those. Okay, so sorry about that. Now we still have two more rules. So the last one that's sort of difficult to master is exportation. Okay, and exportation tells us that these two statements are logically equivalent. So if you have P and Q horseshoe to R, then that's interchangeable with P horseshoe Q horseshoe R. P horseshoe Q horseshoe R. So if P, then if Q, then R. Is illogically equivalent to P and Q horseshoe R, and so you can think that this gets exported, as it were, it gets pulled out, and the horseshoe goes in its place. So this is a very nice thing, and of course that's nice because this is going to turn out to be a way to set up modus ponens. If you want to use modus ponens on this, you would have to have the horseshoe, and so maybe you don't have P dot Q, and so maybe you do have P, and you can export it, and then you could derive Q horseshoe R, and that may be useful in various ways. So those are our four main rules: transposition, implication, equivalence, material equivalence, and exportation. But we need one more rule because of the technicalities, and that's the tautology rule. And I'll write this over here, tautology. And the tautology rule tells you that these two statements are interchangeable. If you have P, then you can write P wedge P. Okay. And if you have P, you can also write P dot P. Now, why would you ever need to do that if you have P or P? Well, clearly, if P is true, then P or P is true. And if P is true, then P and P is true. And that you can see, well, they have the same truth values. So if this can only be true and that can be false, then the two cases are either if this is true, then of course this statement will be true. True and true is true. And if this is false, then that statement will be false. And of course the same is true here. So you don't change anything, but for technical reasons, we sometimes need to use these rules. And so, okay, now I wish I could say this is all that we needed, but we'll find out that when we come back next week, we still need to add a couple more things to this. They're not exactly rules in the same way, but they are important nonetheless, and we will discuss them. But for now, this is enough for us. So let's go ahead and try to illustrate the use of these proofs. Now here's an interesting one. Suppose that someone said it's not the case that A, and they told you that therefore A horseshoe B. Now you might say to yourself, gee, that's interesting. Why would it be the case that if it's not the case that A, that it follows that if A then B? But this is a valid argument. And we can see pretty quickly how to use our rules here. And the rule that probably is going to be most useful here is addition. And that's because when you look here at A horseshoe B, you don't see B anywhere. There's only one premise. So we can see what we need to do is add B here. That's the only thing we can do at this point. And so we write our second premise as tilde A wedge B. And we got that from line 1 by addition, which allows us to do that. Because if this is true, then this statement will also be true, which is what we're doing when we write it down. But now notice that by our implication rule, tilde A wedge B is equivalent to A horseshoe B. That's just what the rule says. So we write down line 3, and we write A horseshoe B, and we got that from line 2 by implication. So this is a valid argument, but notice it's very interesting that it's a valid argument, because in effect, one way of reading this is that it says, if A is false, then A implies any statement that you want. And that's a very strange thing. It's a way of bringing out one of the oddities in the truth functional way of handling implication, or the horseshoe operator, or the if-then statement. Because suppose that my name is not Albert. Okay, so suppose that I am not named Albert. Is a true statement. It's not the case that A, my name is Albert. But then it follows from that if my name is Albert, then I'm a millionaire. That's a very strange thing. Why should it be the case that simply my thinking that something, why should it be the case that something merely being false in this way implies that it being true, although it isn't true, but if it were true, this is saying that the implication is a good one. That's sometimes called the paradox of material implication. And it really is just a way of formalizing or capturing the truth tables, which you may recall for this, have the peculiar property, that we assign true to these two rows of the truth table. So if this thing is false, then the statement always turns out to be true, and that's basically a way of capturing this. If the antecedent is false, if it's true that the antecedent is false, then the statement implies anything, and that's a very strange thing. But again, remember, the argument for why we assign the truth values here in the way that we do is so that we preserve the thing that we think is on firmer footing, which is our intuitive grasp of what it means to reason according to modus ponens. Okay, so that's a very interesting thing here. Let's try another one just to illustrate how to manipulate these symbols. This one's from the book. So it says F horseshoe G. That's one of our premises. Our second premise is F wedge G. Our conclusion is therefore G. So we need to figure out some way to connect up here so that we can get G from our conclusion. And let's see how we do that. So let's see what we can do. Well, let's see what we can do here. One thing that we can see that we can do right off the bat is we can turn this into a condition, and that might give us a way of dealing with this. So let's do line 3 here, and we'll convert this F to tilde tilde F using our rule double negation. Tilde tilde F wedge G from line 2 by double negation. So all we did was turn that into that. And the reason we want to do that is because we want to use our material implication rule, which tells us, remember, that if you have P horseshoe Q, that's logically equivalent to tilde P wedge Q. Okay? These are logically equivalent statements, and of course it goes the other way as well. So if you have tilde P wedge Q, that's logically equivalent to P horseshoe Q. But notice here, what we have is tilde P, and you can think of this as a tilde P right here, where the tilde is negating this term, which you're considering as the P, wedged to G, and our rule says when you have tilde a P wedged to something, you convert that, you take the P, take the negation sign off, you put the horseshoe in there, and you leave that the same. So what we can do is change that into a horseshoe operator on line 4, and what we would get is tilde F horseshoe G. And we got that from line 3 by implication. Okay, so now we have tilde F horseshoe G. Now we have tilde F horseshoe G. And we want to connect it up to this again, remember, but we don't have anything. We have F horseshoe G and tilde F horseshoe G. So that sounds interesting. So it looks like we're on the right track, because it looks like what we're finding out here is that whether F is true or not doesn't matter. If F is true, then you get G, and if F isn't true, then you get G. That's basically what our premises is telling us here. So it looks like G should follow from these two premises. We just have to figure out how to do it. And we've got to turn this into a conditional that connects up to this in a kind of technical but clever way. So here's how we do it. We can go to line 5, and we're going to repeat the procedure up here. We're going to double negate this. So we're going to change that to tilde F horseshoe tilde tilde G. And that we got from line 4 by double negation. Double negation. So now we have that, but now we can use our transposition rule, because remember, transposition tells you that if you have P horseshoe Q, that's logically equivalent to tilde Q horseshoe tilde P. You flip them and put the negation sign there. So we can do the same thing here. We can flip them and put the negation sign there. So using this rule on line 5, we would write down line 6 here, And remember, we flip them, so it's going to be G horseshoe F something. Remember flipping them here, but we're moving in this direction because we have tilde F horseshoe tilde G here. And so what we get when we flip it is you take off the negation signs, and what that leaves you here is tilde G horseshoe F. Tilde G horseshoe F. And we got that from line 5 by transposition. Tilde G horseshoe F. Okay, so that's very interesting. But now we have a way of connecting these by hypothetical syllogism, because we have something horseshoe F and we have F horseshoe something. Okay, so hypothetical syllogism, remember, tells you if you have P horseshoe Q and if you have Q horseshoe R, then that allows you to infer P horseshoe R. And so we want to use that rule on lines 1 and line 6 right here, and that will allow us to say tilde G horseshoe G. 7, and we're going to write tilde G horseshoe G, and we got that from line 1 and line 6 by hypothetical syllogism. 1 and 6 by hypothetical syllogism. Okay, so that's nice. Now this clearly has a weird sound to it. Tilde G horseshoe G, if not G, then G. That's a very strange thing to say, but actually that's logically equivalent to by our rule, material implication, which says if you have P horseshoe Q, you can turn that into not Q or P. So let's go ahead and do that. And we write down line 8 here, and it's going to be not P or P, and we got that from line 7 by implication. Okay, so now this we can get rid of, and we can write down line 9, G wedge G, and we got rid of that by using double negation on line 8. And now we have this statement here, G or G. And this is, of course, why we need the tautology rule. Because you might think, why did we need to have a rule that says if you have G or G, you can infer G is the case? Intuitively, that's the case. But we need a rule that allows us to do it, because even though we can see that G wedge G, somehow G's got to be true if that's true, and we just showed that that's true if these are, so assuming that those are. So we've got to have some way of capturing that. And our tautology rule allows us to do that. When you have this, you can write line 10, and you infer G from that, and you got that from line 9 using tautology. Okay, so now you're done with the proof, and you've shown that G does in fact follow from these two premises. If F, then G, and then F or G are your options there. Okay, so that's very interesting. Let's go ahead and do another example here, one that's slightly more complicated. This one also comes from the book. So here we have our first premise, and it says M horseshoe N, M horseshoe N. And then we have our second premise, says M horseshoe O. Then we have our third premise, it says tilde M wedge N, tilde M wedge N. And our conclusion over here is M horseshoe N dot O. M horseshoe N dot O. And these are in parentheses. Okay, so that's very interesting. Now remember what we want to do. We basically always start the same way when we have a situation like this. And the way that we start is we look at the conclusion and we look at our premises and we try to connect the two. So here we see M horseshoe N dot O. Okay, that's very interesting. And we look and see if there's any kind of obvious ways that is M horseshoe O? Is that yes, M horseshoe O. We look and see if there's any obvious ways. We see M horseshoe N. Okay, we see M horseshoe O. Okay, but we don't see anything that looks like it would follow immediately. It looks like we can get O if we have M, and we can get N if we have M, and then we might be able to dot those together and show that that shows somehow. So nothing really presents itself as immediately obvious. So we want to look at this and think about our rules of replacement and see if there's any way of transforming it into something that looks like it could be derivable from this, because it's not clear immediately what we would do. Well, actually, let's just start messing around before we do this. So one thing we see we can do is this tilde m wedge n looks like it can be turned via implication into a horseshoe. And so we would write down line 4, tilde m wedge n is equivalent to m horseshoe n. Okay, I messed up here. I can see already right off the bat. Okay. Let me start over. So let's take another example. Let's take another example here. So our first premise is m horseshoe n. Our second premise is m horseshoe o. And our conclusion is m horseshoe n dot o. N dot o. Okay, so we have our two premises and a conclusion here. And well, the first thing we do is we look and see if there's any obvious way of getting this out of here. And it's not exactly clear what we would do. Now, one strategy for dealing with these kinds of things is thinking about the conclusion here and what you can do to that and work your way backwards. So look at the conclusion here. And let's just play with it for a second and see what we can get it to do. We have m horseshoe n dot o. Okay, so what could we do with that? Remember, we can't do anything with our, remember, we can't do anything with our rules of implication because it's just one line. And you need at least 2 lines to use any of these. But we can transform it in any way we want using our rules over here. And so what could we do with this? Well, it's a horseshoe right there. And there's only a couple rules that we can use on horseshoes. So we could do transposition, we could flip it around and see if that did anything. We could do implication, turn it into a disjunction. We could do exportation, well, not quite, because this isn't on the other side, although that might work. Well, let's just see what would happen if we used our material implication rule. Well, that would turn this into a disjunction, and we would have tilde m wedge n dot o. Okay, so that's just by turning this conclusion into a disjunction using our implication rule. So that looks interesting because now we have a tilde m wedge n dot o. And you might ask yourself, do we have any rules hanging around which tell us what we can do when we have a wedge and a dot in the same operator? And of course, there is a rule. So we have our distribution rule, which tells us when we have p wedge q dot r, that we can distribute this p, and what we get is, from p wedge q dot r, is p wedge r dot p wedge q. That's what happens when we distribute, and so we can distribute this term here and write down a statement like that. And we would do tilde m wedged to n, and that would then become dotted, which becomes the main operator, to tilde m wedge o. Okay, so now we've used distribution on this, and we say, aha, we can distribute this m, and we get this dotted statement. Now, was there any way that we could get these out of that? Well, we can see by material implication that this really says m horseshoe n dotted to m horseshoe o. And in fact, now we see, well, those are the premises. Those are the premises. So now we can just work backwards. This is the conclusion, and we work down to this step here, but now we see a way to work from there to get to the conclusion. So let's just go and apply what we've learned. Crucially, distribution is going to save us here and help us prove this. So what we have to do is convert these to disjunctions. So let's go ahead and do that. Write down line 3. We may as well do this one first. rewrite tilde m wedge n. That came from line 1 by implication. Okay, then we write down line 4. Do that to this line. Tilde m wedge o from line 2 by implication. Now we have to use our conjunction rule to combine these. So we write line 5, and we have tilde m wedge o dot, excuse me, I want to do it the other way, tilde wedge n. We could do it either way, but this is the way that helps us. Otherwise, I'd have to have another step where I reverse this, and so why do that? And we did that, of course, from lines 3 and 4 by conjunction, 3 and 4 from conjunction. And now we've set ourselves up to do what we want, because now we can use our distribution rule, which says, remember, that if you have P wedge Q dot R, that's logically equivalent to P wedge Q, moving that inside, dotted to P wedge R, or vice versa. You can move back and forth. So now we have our wedge dot statement. We can write this statement, taking the M out, as it were, and putting it in front, so that we get tilde M wedge dotted to the two things inside, which are N dot O. And we got that from line 5 by distribution. But now we know by implication that this is a conditional statement right here, equivalent to 1. So we can write M horseshoe N dot O, and we got that from line 6 using implication. So sometimes when you see these arguments written out, and it's not at all obvious what you're supposed to do, you just need to think about the rules and start messing around with this stuff. What can you change this into? It's not always going to be fruitful. Sometimes you might end up at a dead end. You say, I can change this into that. It doesn't help you. So you can always use the rules, and in Applia, it will let you chase down many false pathways if you want, because there's nothing wrong. The rules say, if this is true, you can write down that other statement, and that will be true as well, and that's perfectly fine. But it won't always help you get to the conclusion. So you need to be thinking strategically about how it is you start and get to where you're going. And sometimes, obviously, just like working in a maze, it's more convenient to start at the end and work your way backwards. Okay, so let's do another example. Let's do another example. And this one comes from the book as well. So here's our first premise. The first premise here is tilde S horseshoe K, tilde S horseshoe K. Our second premise is S horseshoe R wedge M, R wedge M. And our conclusion is tilde R horseshoe tilde M horseshoe K. Tilde M horseshoe K. Okay, so those are our two premises and our conclusion. We do the same thing we always do. We look and try to see what we can get out of these premises. Well, again, it looks like, well, if S is false, you get K. If S is true, then you get R wedge M. And what this tells us is we want to try to figure out tilde R horseshoe tilde M horseshoe K. And so it's not exactly clear how we're going to get this conclusion from those premises. So what we want to do, just as in the previous case, we want to deconstruct this conclusion and see what we can do with it. So we take tilde R and we horseshoe it to tilde M horseshoe K. And now we think about our rules. One thing that kind of sort of jumps out right at the front is that we have a horseshoe to a horseshoe. And there is a rule here which looks like it would deal with that. And that's the rule that says if you have P dot Q, which is horseshoe to R, then you can, that's logically equivalent to P horseshoe Q horseshoe R. That's our exportation rule. And so it looks like what we have here is a version of that. If you have P, horseshoe Q, horseshoe R, P, horseshoe Q, so if that's our P term, that's our Q term, K is our R term, then it looks like we should be able to write this other statement down, P dot Q, horseshoe to R. And so let's try that. We have our P, and we have our Q, and that's horseshoe to R. Okay, so that's very interesting. We have here tilde R dot tilde M, and we sort of know a rule which allows us to deal with those kinds of expressions. That's De Morgan's rule. So remember, De Morgan's rule says that if you have tilde P dot Q, this is the conjunction version, then you get tilde P wedge tilde Q. But on the other hand, if you have tilde P wedge R, Q, then what that's equivalent to is tilde P dot tilde Q. And so now we see tilde P dot tilde Q basically there. We can change that into a negated version of these two things that are disjoined to each other. So we can write R wedge M. That's interesting. Horseshoe K. And of course, that's interesting because we see R wedge M right there. Now we see this, and so we figure out, what could we do with that? Well, I'm not sure. Let's use our rules and see what we can do. Well, one thing, this is negated. Okay, so let's flip it around using transposition. So remember, transposition says if you have P horseshoe Q, largely equivalent to tilde Q horseshoe tilde P. So that's very interesting. So we could change this, and then we get tilde tilde K out of it using our double negation, tilde R wedge M. That's very interesting because now it looks like we have tilde Q horseshoe to a tilde P. So if this is our P term, this will be our Q term, tilde tilde. We flip them and take off the negation. What we get is tilde K horseshoe R wedge M. Interesting. And now we see something up here which looks like it would connect to that. Because this is tilde S horseshoe K, we could flip that around. And we would end up essentially, after we're done, with tilde K horseshoe S. So if tilde K, then horseshoe S. And if S horseshoe R wedge M, then we see we can get tilde K horseshoe R wedge M, which ultimately would lead us to the conclusion here. So what we've done here is we've looked at the conclusion, we've played with it a bit, manipulated the symbols according to the rules, until we get something which looks like it can be connected to the premises that we have using these rules that we just did. So let's go ahead and work out the proof then, now that we have a strategy. Let's write it down. Okay, so we know what we have to do. We want to use transposition, and we want to flip premise 1. So we write down line 3 here, and we're going to flip those, and that's going to give us tilde K horseshoe tilde tilde S, and we got that from line 1 by transposition. Okay, so that's very exciting. We want to get rid of this by double negation. So we write down line 4, tilde K horseshoe S, and we got that from line 3 by double negation. So now we have tilde K horseshoe S, we have S horseshoe R wedge M, and that gives us the thing that we wanted, which is tilde K horseshoe R wedge M. Okay, so that's very exciting, and we got that from lines 1 and lines, we got that from lines 2 and lines 4 by hypothetical syllogism. Lines 2 and 4, hypothetical syllogism. So now what we need to do is remember how we got to the conclusion using those reverse engineering steps. And I think what we did was first we got to flip this around. So using transposition again, so we write down line 6, and we're going to flip, and we write tilde R wedge M, horseshoe tilde tilde K, and we got that from line 5 by transposition. All right, so we gotta use De Morgan's rule here, and we need to use our double negation there, and we can do them in either order, but let's just do double negation first because it's right there. It doesn't really matter, remember. So what we have then is tilde r dot tilde q, excuse me, tilde m, which is what's there, and that's going to be horseshoed to tilde tilde k. You have to do them in 2 steps. You can't just do it all at once, even though obviously we can see how it can be done all at once. You need to show different steps. So we use De Morgan's on line 6 to write that. Now we're going to use double negation over here. We're well on our way to doing what we want. We write down line 8, and so we write tilde r dot tilde m, and that's horseshoe to k, and we got that from line 7 by double negation. Okay, so now we've got exactly what we wanted, and we need to use our exportation rule to take the tilde m out and horseshoe it to k in the way that we want. So exportation tilde r horseshoe parentheses tilde m horseshoe k, and we got that from line 8 by exportation, and now we're finished. So again, a useful strategy here is just becoming comfortable using the rules so that you can just look at a string of symbols and start playing around with it. It may lead somewhere interesting, it may not, but you need to get in there and you need to start manipulating these things and becoming comfortable simply saying, aha, tilde p wedge q, that's there, or vice versa, okay? And that's something that only comes with a lot of practice and really sort of internalizing these rules. Okay, so let's do another example. These examples are good. So our first premise here is k horseshoe m. Our second premise here is L horseshoe M. And our conclusion is K wedge L horseshoe M. So you can see that this should make sense because this says if this is true, if you have K, then you have M. This says if you have L, then you have M. So it looks like, well, if you have either K or L, you have M. So it seems intuitively like a good argument, but what we want to do is prove it. Now, of course, just as before, what we see here is that, there's no obvious way that this is going to come using our rules here, so we can't use any of them to get at what we want. But if we start thinking about how to deconstruct this, we can see that there are various things that we can do. So let's take our conclusion down here and just see what types of rules can be applied to it. So it's a conditional statement. So we need to use rules that are going to do something with conditions here, with conditionals, I'm sorry. And so one thing we can do is use implication, turn this into a disjunction here. And that would give us the following thing. So if you use, remember, implication says tilde p wedge q is equivalent to p horseshoe q. So p, think of this term as the p term, horseshoe to q, then we can use our rule here, and we would write down tilde this p term, k wedge L, and that's going to turn into a wedge itself, and that's wedge to M. Okay, so now we can move this in with De Morgan's rule, and what we know is that a negated disjunction is equivalent to each of these terms being negated in a conjunction, and that's wedged to M. Now we see a familiar pattern. We see a dot and a wedge, and we know that our distribution rule is something that applies to dot and wedges, but of course we'd have to flip this around, so we'd have to have M wedge tilde K dot tilde L there, and now we could do some distribution on that, and we know that when we have M wedged to a dotted term, we can distribute the M into it, and what we end up getting is M wedge tilde K dotted to M wedge tilde L. M wedge tilde L. Okay, and there's a dot there, and we can break these apart. Now, of course, I hope you can see that this is a conditional statement. If you flip the tilde k around, so that says tilde k wedge m, don't make me write that down, then that really says k horseshoe m, which is our first premise. And if you flip this around, this says tilde l wedge m, and that's really equivalent to l horseshoe m. So really, all you have to do is change these using implication, and join them, and work our way backwards in the way that we've just shown. Okay, so once again, taking the conclusion and working around with it until we get the thing that connects to the premises, a very valuable strategy, one that we use over and over again in constructing these proofs. So let's go ahead and do that. So we're going to write down line 3 here, and we'll use material implication, tilde k wedge m from line 1 by implication. We'll do the same thing here, tilde l wedge m by implications from line 2. Okay, so now remember, we're going to have to flip those around because we want m to be a place where we can use distribution on it. So now, although it's a pain in the neck, we're going to have to write down these 2 lines where all we do is flip these around. So we're going to have m wedge tilde l from line 3 by commutativity, which says you can flip them, and then we'll have m wedge tilde k. Sorry, this we got from line 4. I gotta be more careful when I'm speeding through this stuff. And this one we got from line 3 by commutativity. Okay, so now we can conjoin these, and that's going to set up our distribution. So we write line 7, and we have m. We want k wedge l, so we'll do k first. M wedge tilde k. M wedge tilde k there. That's going to be dotted to m wedge tilde l. M wedge tilde l. Okay, and we got that from line 5 and 6 by conjunction. 5, 6, conjunction. Okay, so now we can use distribution, which says that if you have this, remember, you can take the m out. The wedge becomes the main operator, and these 2 things get dotted together. So we write down line 8, we have m wedge, that's the main operator, and then we have these 2 things dotted together, so we have tilde k dotted to tilde l. Okay, and we got that from line 7 by distribution. Okay, so that's very exciting, and now we can use De Morgan's rule here, and we see that line 9 then becomes m wedge tilde k wedge l. Okay, so now we have tilde that, and remember what we want to do is get this k wedge l horseshoe m, and now we have it, but it's not in the right order. So we've got to write line 10, we got to use commutativity and flip them around, and we write tilde k wedge l, and we're going to wedge that to m. We just flip those around. We got that from line 9 by com. And we got this from line 8 by De Morgan's. I'm not keeping good track here. Hopefully you keep better track. Obviously, Applia forces you to, but in general, I want to make sure that anyone can look at this and follow it. And now we can use our material implication rule, which says if you have tilde p wedge m, that's equivalent to p, which is this term, horseshoe to m. There we go. And that's the conclusion. And we got that from line 10 by implication.